Good morning, good evening, good afternoon, and welcome back to another math lesson. Today we're going to be wrapping up our unit on rational functions by doing lesson number 3, sketching graphs of rational functions. Okay, so let's get started. When sketching the graph of a rational function, the following are required when applicable. Okay, vertical asymptotes, horizontal asymptotes, 1 point in each section. Okay, that's a minimum. Okay, you need at least 1 point to help graph. You need to graph the asymptotic behavior and the point of discontinuity. Okay, I mean the vertical and horizontal asymptotes we've already talked about. At 1 point minimum in each section, so we can kind of say that's on either side. Okay, of the vertical asymptotes. That's what I mean by each section. Okay, so on either side of the vertical asymptotes, you need at least 1 point on each side. Okay, asymptotic behavior. So what that means is you're just following along the asymptotes. Okay, so that's the asymptotic behavior. You're just graphing. Your graph should follow the your vertical and horizontal asymptotes. Okay, and then obviously you need to find your point of discontinuity. Okay, steps to sketching. Okay, so this is important to know. Step number 1: factor the numerator and denominator. Okay, determine any vertical or horizontal asymptotes and or holes. So again, I personally like to do horizontal asymptotes first so that it's easier for us to determine where they are before we even factor. Okay, so I would actually do the horizontal asymptote first before actually factoring, but again, it's personal choice. Okay, find the vertical asymptotes and the holes. So find their NPVs, right? Use those NPVs to figure out if it's a vertical asymptote or a point of discontinuity. Find your x-intercepts. Okay, set y to 0. Find your y-intercept. Set x to 0. Use substitution or table of values to find 1 point in each section to determine the behavior of the function near the asymptotes. And finally, use smooth curves to complete the graph. Okay, so some students ask me, hey, if I find the x-intercept, does that count as a point in either section? No. Okay, so it would be preferable if you also add another point in each section. Okay, so make sure you find the x-intercepts, you find the y-intercepts, okay, if there's any, okay, and you add a point on either side. Okay, so it's in there, it's step 5, so make sure you add another point as well. I can't stress that enough. Okay. This brings us to the basic shapes of rational functions. Okay, so each of them have a special name to them. Okay, so sketch the first one is a hyperbola. The next one is an inverted funnel. Then we have a speed bump and then an H shape. Okay, so your hyperbola is 1 over x. Your inverted funnel is 1 over x squared. A speed bump is 1 over x squared plus 1. And then finally, you have your H shape, which is 1 over x squared minus 1. So these are just examples and basic shapes of how they'll look. Okay. So let's go ahead, let's draw a few and draw this one, a hyperbola. So again, this is the same idea, okay, as what we did before. So you have your, this is your reciprocal function that we talked about in lesson number 2, part 1. Okay, so you have your asymptotes there, and then the graph will look something like this. Okay. So this is called a hyperbola. Very similar to how we started graphing in lesson 2, part 1. Okay. The next one is called an inverted funnel. Okay. So it's going to be your inverted funnel will have, again, your vertical asymptote, right, at x is equal to 0. Horizontal asymptote at y is equal to 0, all characteristics that we learned about in the second lesson, part 2. But your inverted funnel will have both the, will have your graph in the top half. Okay, because in this case, when you have 1 over x squared, all of your y values will be above 0. Okay. So that's what's called an inverted funnel. Okay, the next one's a speed bump. You have seen this before. Was one of the examples that we did together in lesson number 2, part 1, I believe. Okay, so it looks, in this case, because of the x plus 1, or the x, because of the +1 in the denominator, there will be no values, okay, that actually of x that will equal 0. Okay, so your denominator cannot equal 0. Because your denominator cannot equal 0, right? You do not have any vertical asymptotes. Okay, so because of that, it's going to create this shape. So you will follow along the asymptote, come up, hit your point, come down, and carry on. Okay, that's what a speed bump is. Okay, and then finally, the last one is the H shape. So you have the 1 over x squared minus 1. So I should still have room for that. Yes, I do. Okay, so the last one, this one will have asymptotes. Okay, it'll have asymptotes at x is equal to 1 and x is equal to -1. Okay, it'll also have a horizontal asymptote at y is equal to 0. Okay, so this is your H shape. So essentially what's going to happen is, and we did an example like this as well in lesson number 2, part 1, but this is what it's called, an H shape. So you're probably wondering, well, what do you mean? These graphs don't look anything like a shape. If you look at the asymptotes, so the ones in orange, it kind of looks like an H. Okay, so because of that, that's where this H shape comes in. Okay, so these are all the different shapes that can be made, okay, for these particular rational functions. Okay, so you have your hyperbola, your inverted funnel, your speed bump, and then your H shape. Okay, so with the examples that we'll do, I'm only going to do a couple of them. Okay, just to try and get an example of what the hyperbola looks like, what the speed bump looks like, what an H shape looks like, what an inverted funnel looks like. Okay, so we'll try and do one of each of how they look and how they graph, and we'll go through all the steps in order to graph. Okay, so those are the examples that we'll go through. All right, let's try example number 1. So example number 1 says, sketch f of x is equal to x squared minus 4 divided by x plus 2, and we're going to state the domain and range. Okay, so with the steps to graphing, it does say to factor first. Me personally, I like to do the horizontal asymptote first, just to get it out of the way. Okay, so then we can go ahead and we can graph that as well. Okay, so right away we can see that this is the degree in the numerator is greater than the degree in the denominator. So we will have an oblique asymptote. So there is no horizontal asymptotes. Okay, so in this particular example, there are no horizontal asymptotes because the degree in the numerator is greater than the degree in the denominator, and that's from the characteristics we learned in lesson 2, part 2. Okay, so now let's factor. So we have f of x is equal to x plus 2, x minus 2 divided by x plus 2. Let's state our NPVs, so the non-permissible values. Okay, so those are at x is equal to -2. The x plus 2's cancel. So all we have left is f of x is equal to x minus 2. So right away we have a linear line. Okay, so from that we can now determine the point of discontinuity. So let x is equal to -2. So that means that f of -2 is equal to -2 and minus 2. So that means that f of -2 is equal to -4. That means the point of discontinuity, okay, is at x is equal to -2 and y is equal to -4. Put them together as a point, -2 and -4. Okay, so let's go ahead and let's graph this. Okay, 1, 2, 3, 4. Right, 1, 2, 3, 4. Again, when you're sketching, right, you have to create your own coordinates sometimes. Okay, so and just state that if this is 1, this is 1 as well, so that the reader knows exactly how much your scale is going up by. Okay, so let's create this graph of x is equal to -2. So, or sorry, f of x is equal to x minus 2. Okay, so that means your y-intercept is going to be down at -2 to start. Go blue. Okay, which means we'll have our x at our x-intercept is going to be at 2. Okay, again, you can find that as well, right? To find the x-intercept, right? You set y is equal to 0, right? That's part of the steps that we do. So it's going to be 0 is equal to x minus 2, which means that x is equal to 2. For your y-intercept, right, you set x is equal to 0, so y is equal to 0 minus 2, which means that y is equal to -2. Okay, so now that we've graphed those 2 points, one thing we got to remember is we have a hole at x is equal to -2 and -4. So there is a hole in the graph there. You draw the points there and then further down. So your graph will look like this. Hits the point and then carries on. Make sure you draw arrows at the end to signify that your graph continues in this particular direction. Lastly, we need to say the domain. Okay, so the domain is x such that x is an element of the reals, provided that x cannot equal -2. And finally, the range. Okay, so the range is going to be y such that it's going to be y is everything, but y cannot be -4. Okay, so that's how you would do this particular example. Again, find your horizontal asymptote, find your non-permissible values, right, by factoring. Okay, cancel anything that needs to be canceled, find your points of discontinuity, find your vertical asymptotes, right? In this case, it was easier for us to graph because it was a linear line, so I didn't really need to find any points on either side of the asymptotes because it's just a linear line. Okay, so it's much easier for us to graph. Make sure you draw the point of discontinuity in the correct spot. Okay, and that's how you do this particular example. Moving on to example 2. So this shape is going to look different. Okay, so we're going to make sure that we go through the same steps as before. Sketch f of x is equal to x minus 3 divided by x squared minus 2x minus 3 and state the domain and range. Okay, first off, again, I personally like to do the horizontal asymptote just to get that out of the way. So we look at the degrees of the numerator and denominator. Okay, so the degree in the numerator is 1 and the degree in the denominator is 2. Because of that, we have a horizontal asymptote at y is equal to 0. So let's go ahead and let's graph that. At y is equal to 0. Okay, that's our horizontal asymptote. Next, we can move on to factoring. So f of x is equal to, so we have x minus 3 all being divided by, okay, so we have x squared minus 2x minus 3. That factors to x plus 1 and then x minus 3. Okay, so before we cancel anything, we can say that the non-permissible values, okay, they're at x is equal to -1 and +3. Okay, now we can cancel. So we have the x minus 3's cancel. So these cancel right there, which means all we have now is f of x is equal to 1 over x plus 1. So this should look like a hyperbola because this is how it is set up. Okay, but now we can safely say that there is a vertical asymptote now at x is equal to -1. So we can go ahead and we can graph that. Okay, so let's just add some points here. Okay, so let's go ahead and let's add the vertical asymptote at x is equal to -1. So here is our vertical asymptote at x is equal to -1. Okay, so let's add in some points as well to say, hey, this is going up by 1, the y's are going up by 1, and the x's are going up by 1. Okay, the next step we need to do is we need to solve for the point of discontinuity. So we're going to say let let x equal 3. Okay, that was the other non-permissible value that wasn't used. Means f of 3 is going to be equal to 1 over 3 plus 1. So it's going to be equal to 1 over 4. So that means, I'm just going to write it in green again. The point of discontinuity is at 3 1/4. Okay, so that's where the point of discontinuity is. So let's go ahead and let's graph that. And I'm going to put it in green just so that we know where it is. So it's going to be a 3. So 1, 2, 3 1/4. So it's about there. Okay. We need to find a point on another point on either side. So since we found the point of discontinuity on the one side, that counts as a point. Okay, so we can also find the y-intercept. So let's go ahead and find the y-intercept. So y-intercept, we said x is equal to 0. So again, y is equal to 1 over 0 plus 1, which is equal to 1. So that means the y-intercept is going to be at 1. I can put that there. Okay. Now let's look for a point on the other side. So what do I mean by the other side of the asymptote? Well, since the asymptote is at -1, I mean, I would just choose the next point being at x is equal to -2. Okay, so that signifies that we're on the left side of the asymptote. Okay, so let's set x to being at -2. Okay, so that means that f of -2 is equal to 1 over -2 plus 1. So it's equal to -1, right? Because -2 plus 1 is -1. 1 over -1. 1 over -1 is -1. So at -2, it's here. Okay, so we have all the points we need. Okay, so now we can go ahead and we can graph. All right, so it's going to follow this. So again, the smooth curve, we're going to get into that point. We're going to hit the point, but not go through it like so, and it'll keep on going. That's the one part. The other part that we'll graph, okay, it'll hit the point at x is equal to 2, and it'll follow the asymptotic behavior. Okay, so there you have the drawing of this particular graph. We found the horizontal asymptote, we found the NPVs, the vertical asymptote, we found the point of discontinuity, we found the y-intercept, and we found another point on the other side of the vertical asymptote. Okay, last thing we need to do is the domain. Well, the domain is going to be everything, right? X is an element of the reals, provided that x cannot equal 0 and 3. Okay, and your range, well, that's y can be everything, but y can't be, oh, sorry, I have to change that. X can't be -2. X can't be -1 and 3, and y can't be 0 and 1/4. Okay, so there you have it for this example. We did the domain and range, found the horizontal asymptote, NPVs, vertical asymptote, point of discontinuity, y-intercept, and another point on the other side. Lots of work that needs to be put into this, but we have all the necessary information necessary. We have all the information necessary to graph. Moving on to example 8. Okay, so a lot of you are wondering, well, what happened to the rest of the examples? The other examples that I have are very similar to the ones that were previously done, examples 1 and 2. Okay, so you can go ahead and you can try those out on your own. So make sure you do so, compare with others to see what you got as well. So example 8. Sketch f of x is equal to 2x squared divided by x squared minus 4 and state the domain and range. So again, how I like to start is do the horizontal asymptote. Okay, so you look at the degree of the numerator is x to the power of 2. The degree of the denominator is also 2. So you take the coefficients. So the horizontal asymptote is going to be at y is equal to 2 over 1, which is 2. So that's our horizontal asymptote. So let's go ahead, let's make some points. Like so. And we can add it in. Here is our horizontal asymptote. and y is equal to 2. Okay, so y is equal to 2. Oops. 2. Okay. Next up is we factor. So we have f of x is equal to 2x squared divided by, well, this is x plus 2, x minus 2. So in this case, we have NPVs, and they're at x is equal to positive or negative 2. Okay, and then finally, we have, because there are, nothing cancels. Because nothing cancels, that means we have vertical asymptotes at x is equal to positive or negative 2. So let's go ahead and let's plot those in. Okay, so here's x is equal to negative 2. And then x is equal to positive 2. Okay, so right away we can kind of look at it and go, well, wait a minute, we've seen this kind of graph before. It looks like an H shape. Okay, so your asymptotes kind of look like an H. So that's what our graph will look like. Now, we can go ahead and we can find certain points. Okay, some points being your y-intercept and your x-intercept. So let's go ahead and let's find those. Okay, so let's find the y-intercept first. So that we're going to set x is equal to 0. Okay, so because of this, f of 0 is equal to 2 times 0 squared over 0 squared minus 4, which is equal to 0 over 4, which is 0. So we have an intercept at 0, which also would be our x-intercept. Let's confirm. So x-intercept, okay, is when y is equal to 0. So we have 0 is equal to 2x squared over x squared minus 4. We'd have to multiply the x squared minus 4 by 0, but that makes it 0. So 0 is equal to 2x squared, which means that x is equal to 0. So good. Our y-intercept is at 0, okay, and our x-intercept is also at 0. So that's one set of points there. Okay, we need to find points now on the far left side and the far right side. So the left side of x is equal to negative 2. I mean, what I would do is just go to the number directly next to it. So x is equal to negative 3. So let's try that. Let's do x is equal to negative 3. So we have f of negative 3 is equal to 2 times negative 3 squared, all being divided by negative 3 squared minus 4. Okay, so 3 squared is 9, right? 2 times 9 is 18. So we have 18 over, this is 9 minus 4 is 5. So it's 18 over 5. So that means at negative 3, it'll be at 18 over 5. Okay, so that's what, 3 3/5? So, I mean, you do the best you can. You kind of guesstimate on where it's going to be. Okay, so let's put that, we did that in blue, let's make it in green. Okay, so negative 3 and 3/5, so it's just, so this is negative 3, here's 3, and both 3/5 is both, I'd say there. Okay, and we need to set it now on the far right side, so we're going to do the same thing, but at x is equal to positive 3. Okay, it'll actually give us the exact same spot. Okay, so again, let's confirm. X is equal to 3. So we have f of 3 is equal to 2 times 3 squared, all being divided by 3 squared minus 4. Again, so it's set up the same. 3 squared is 9. 2 times 9 is 18. Okay, and then 3 squared is 9, minus 4 is 5. So it is the exact same. Okay, so it's going to be 3. Okay, and a point there. Okay, we can also choose another point as well. Let's choose the points between x is equal to negative 2 and 2. So I would just say, because we already have x is equal to 0, let's just choose x is equal to 1. Right, just to cover all bases. So if we have x is equal to 1, we have f of 1 is equal to, well, 2 times 1 squared. Squared. Okay, all divided by 1 squared minus 4. So it's basically 2 over negative 3. Right? Right. 1 squared is 1. 2 times 1 is 1. Divided by 1 squared is 1. Minus 4 is negative 3. So this is negative 2/3. So it's going to be 1 and 2, negative 2/3. And it's going to be the same on this side, because it'll make a parabola. Okay? So we have all the necessary information we need. We can now graph our H-shape rational function. Like so. Now, when it asks for its domain and range, okay, let's do it. So the domain is going to be everything but x can't be positive or negative 2. Your y's are going to be a little different. Your y can be everything, right, but 2. And we have a gap in between the y equals 0, okay, and then the y equals 2. So in that area, it won't exist. So your range, okay, is going to be y is greater than 2, but also y is less than or equal to 0. Okay, so those are 2 spots. Okay, provided that y is an element of real numbers. Okay, so we've done everything necessary here. We've found the horizontal asymptote. We found the non-permissible values we factored, right, to find our vertical asymptotes. We found our y and x intercept. We found points on either side of the asymptotes. Okay, and then we graphed following asymptotic behavior and also stating the domain and range. Okay, so we've done everything necessary for this graph. Yes, I understand it is sometimes a lot of work and it's tedious, but this is the amount of work that goes into these kinds of questions. Last example. Okay, so sketch f of x is equal to 4 over x squared plus 4 and state the domain and range. Okay, so what we'll do for this one is we will figure out the horizontal asymptote to start. So the horizontal asymptote, okay, is going to be at, well, since the degree is higher in the denominator than it is in the numerator, it's going to be y is equal to 0. Okay, this x squared plus 4, because of that plus 4 in the denominator with the x squared as well, this is going to be a speed bump, okay, because there are no vertical asymptotes. Okay, because there's no vertical asymptotes, we can't necessarily graph this thing, okay? So what we'll do is we'll find the y-intercept. So let's go ahead, let's find that. Y-intercept. So we're going to set x is equal to 0. So it's going to be f of 0 is equal to 4 over 0 squared plus 4. So in this case, it's going to be 4 over 4, which is 1. Oh, okay. So that makes things a lot easier. So we go 1, 2, 3, 4. And 1, 2, 4. We can draw our horizontal asymptote at y is equal to 0. Okay. And our point there. Okay, so you can find other points as well. Let's go on either side of the y-intercept. Okay, so it's just so that we can see if this is going to be the highest point or not. Okay, so we're just confirming if this is going to be the highest point. So let's choose x is equal to -1. So when x is -1, it's equal to 4 over -1 squared plus 4. Okay, so this is going to be 4 over, well, 1 squared, so this is going to be 4 over 5. Okay. Your f of 1 will also be the same. So it's going to be 4 over 1 squared plus 4, so it'll also be 4 over 5. So we can safely say that the y-intercept is actually going to be the highest point in this case. So that's where we found our speed bump. So let's go ahead and let's graph this. So again, it's going to follow along the asymptote, come up, hit the points, come down, and there we have the speed bump. Okay. Again, stating the domain and range, well, your domain is going to be x is an element of the reals. It can be anything because there are no points of discontinuity or vertical asymptotes, right? There are no non-permissible values. X can be anything. And your range, well, your range is in between 0 and 1. So there you go. So this is an example of a speed bump. Okay. So what I'm going to show you now are the rest of the examples and just how they're graphed. Okay. So if you want to go through them and just pause the video just to check your answers, you can go ahead and you can do that. Okay. But the rest of this will be just me showing you what they are, not really explaining, because you can go ahead and try them out on your own. Okay, that is the end for the lesson on sketching graphs of rational functions. I hope you enjoyed it. Remember, when it always comes to math, keep calm and show your work.